I'm introducing Rana. Rana got his undergrad degree from the University of Florida, his graduate degree from MIT, and he's now a professor at Caltech. And Rana is uniquely qualified to give this talk. This talk is about LIGO, and you'll hear a lot more about what that is. But Rana single-handedly built LIGO, right? Yeah, that's what I thought. Rana he's an experimenter. I'm a theorist. He's an experimenter. So he builds the machine, and then, well, we won't go into the differences between experimenters and theorists, except to say that theorists are better. Okay, but Rana is going to have plenty of time with the microphone, so it's all okay. So Rana helped build this machine. He's an expert on making very, very precise instruments. And arguably, he's helped craft one of the most precise instruments ever built, and we've used it to do this amazing science. So Rana will tell us that story.
So a lot of us in physics, Aspen is a very special place and has been that way for since before I was born. And it's a place where people come to have good ideas. And scientists will tell you a lot. Scientists complain a lot, more or less. And that's what I'd understand. They complain about funding or the weather conditions or that kind of thing. But the real fuel that drives the science in big steps is big ideas. And this is the place where it happens. And I've been hearing ever since I was, 18 years old or something, that Aspen is the place to go if you want to hear what's hot and what's about to happen next year. And we've found that to be true I think this year also. So this is one of the images that I first saw here on somebody's slide, and it spoke to me of what we should be doing. And this is called the spiritual pilgrim, and he's looking around and seeing what he thinks the world looks like, and that there's stars on this shell. But then finally, using some kind of new technique, breaks through and finds out there's some sort of different underlying mechanism, which is what everything runs on. And well, we haven't found that yet, but this is the story of getting there. One of the things that people do to find out how the universe works is look up into the sky. And well, I didn't have any interest in this when I got started. It seemed like an old-fashioned type of science to me at the time. And I thought all that anybody did was look at the visible light, which is what you do when you go in the backyard and use a telescope. As I got older, I found out people also have infrared vision, so they have detectors, and this is what this Milky Way galaxy looks like in the infrared. And I think this is what it looks like in the ultraviolet, and this is what it looks like if you look in gamma rays and so on. And there's all kinds of different radiation you can look at, microwaves and infrared and so on, radio waves. And in each of the different wavelengths, which is like looking at a different color of light, except for it's a rainbow that's something like 200 billion times wider than the rainbow you're used to. It gives you a lot of different pictures. There's a lot of different things going on in different colors. And so the astrophysics I got started in, though, was this one. And you could look at it and say, well, how sad. Or as the way it was sold to me was, well, look, young man, isn't this a fertile ground in which you can work? You can be the first. You'll be famous one day. You should get into this line of work. And that was in 1998. And I was told, it's going to be a long road, sure, and you'll have to work hard, but perhaps by 2002 or 2003, we'll have our first signals. And that sounded reasonable. 4 years, and then you could graduate and become world famous. And then I found out a few years later, the people older than me who had gotten into school at that time had heard that same story, but in the late 80s. And the story seemed as true as in the late 80s as it did at the turn of the century. But let me finish that a bit later. So this is a movie. I didn't know there was sound in that movie. This is a movie, this is our galaxy, and this is the same thing I just showed you, but now it's flipping through the medium infrared, so which is just past red in our rainbow. This infrared is now way past red in the rainbow, and then this is way out into the radio, almost at the types of frequencies you use for microwaving stuff in your oven. And you can see it's the same picture, they're just switching between wavelengths here. You see a lot of different things when you switch the way that you look at things. Here you see this pink trails, and then this sub-millimeter picture just looks like fire, like the galaxy is on fire. I don't understand it, but I like this picture, so I'm showing it to you. I do. There are some parts of this talk I do understand. You can ask me about those, I swear. This is about as mathematical as this will get, so if that's what you like, enjoy it while you can. This is the things we were interested in with this blank sphere that I showed you is gravitational waves. And this has to do with Einstein's view of the universe circa 1915. And there he said, basically, space bends when you put heavy things into it or a lot of energy. And this quote is the most important. It's more important than this equation, maybe. If you have mass, it tells space-time, which is the space-time continuum that you always heard about in sci-fi. Mass tells space-time how to curve, and if the space is curved, that tells you how the mass moves around. And the Einstein equation that equates these two just says, if you have some amount of energy, you put in front of it, you times it by something that has, after the decimal point, it has 43 zeros and then a 1. So it's a really small number. And if you do that, you'll get how much the space is curved. So another way to think about it is, well, if you had a piece of, I don't know, maybe you don't have this. If at home you have a gigantic diamond like this, and you try to, if you've really been working out and you try to bend it, it's not going to bend very much, no matter how much force you put onto it. And space-time is like that, except for it's much, much stiffer than diamond. So you can put huge amounts of energy. You can blow up the whole Earth and put all of that energy into it, and you still will have a hard time detecting the curvature of the space. And so that a little bit tells you why that picture I showed you before was blank. It's extremely hard to measure any curvature in the space-time. Oh, it's the animation. Oh, I don't know what that's for. This is a different slide. Here I've added a little bit more, it looks a little bit more legitimate Einsteinian because it has more symbols, though I would say it doesn't add much more clarity. This is the image I want you to have in mind. This is an artist's impression. This is also sort of an artist's impression. This is done before anyone had ever measured anything with gravity, and this is done after. So here's two balls, with two stars spinning around each other, which are really heavy, and you can see this gridded, the grid of space-time has got curves in it as it goes around, and these kind of waves are the things we are trying to detect. And if we can, we think we can turn the information from the wave back into something which tells us about these two things. And it would be a new way of looking at the universe if this whole story holds up. So those waves, when they come to the Earth, imagine, none of my analogies are any good. First I had this big diamond thing. So here's another ridiculous one. Imagine in empty space, you've put a dozen hula hoops for some reason. These are the kind of things you always get in the physics homework problems. Imagine a dozen hula hoops in space. This is what we have. So there's a dozen hula hoops in space, and the wave comes through, and as the wave comes through, it stretches and squeezes the hula hoops up and down. And so it goes up like this, and it shrinks like that. And that is the distortion of space that we want to detect. And so in order to find something like this is the calculated effect according to the Einstein equations. We need to build an instrument that can measure something like this. However, in this case, you can see the hula hoop it's almost like 100% stretching that it's getting. And the amount of stretching that we estimate we can measure on the Earth from even the most cataclysmic events in the universe would be 1,000 billion times smaller than this. So 0.000, 21 zeros, and then 1. So, you know, a lot smaller than this, I guess I'm saying. A lot of zeros. However, luckily, fortunately, nobody knew that in the 1950s. And they thought those signals, instead of having 21 zeros, would only have 15 zeros. Still seems like a lot of zeros. But one is 1,000,000 times harder than the other. And so there was this guy, Joe Weber, who you can see has the same haircut as me. This is not on purpose. It just we're similar. And he decided there's this hula hoop picture, but I can make a bar like this, and I'll put sensors all across the middle of it. And so when these waves come through, I'll be able to detect the stretching by looking at these sensors, so on. And he tried for some time and thought that he had detected signals, and everyone in the world got really excited about it. But no one could ever confirm his predictions, and we now think there was some kind of problem with the way he analyzed it. But because nobody knew how really hard this field would be, and no one knew what to expect, people believed him long enough to get excited about it, and then a lot of people started working in the area. And, well, that's a fortunate turn of events. If we knew everything at the beginning and how hard it would be, probably no one would have gotten into it, I say. In the late 60s and 70s, Robert Forward, who became a sci-fi writer, and then Ron Drever, Ray Weiss, and Kip Thorne at Caltech, also got excited about this idea, and they put together plans to use not bars like this, but to use lasers and the interference pattern from lasers in order to detect the vibrations of these waves. And they figured bars you can only make so big, but lasers travel really far. So you can make a detector so big that it can capture a lot more of the wave and make a better measurement. That was the plan. It turned out, and I'll tell you why it turned out to be harder than they thought. The way it works, here's the laser, and these two are mirrors, and this is a mirror which lets through half the light and bounces off half the light, and this square here is supposed to represent our detector. Oh, it worked. So that's how it goes. The light bounces back. And we think when the wave comes through, it shakes the space in between these two things and makes the light change when it comes back to our detector. So light's a wave, and the wavelength is a lot shorter than this, but this is good for the animation. The wave goes down to the end and comes back. And when the two waves interfere at this thing and go toward our detector, as long as the waves are out of phase, the two light waves, we won't see anything. But when the gravitational wave comes through, it stretches one arm, and so some of the waves don't cancel the other waves anymore, the electromagnetic waves. And so we detect the signal as a change in the power at our detector. It just goes dark and bright. So that technology, which detects the changing light power, is just the same as a solar cell. It's a semiconductor that turns light into electricity. And except for it's a lot more expensive because we're funded by the government. You don't have to read all this. This is just an artistic representation of time. Here was Einstein in the early 1900s, and around that time, people were also doing the first precision experiments of distance, and which were confirming the basic of Einstein's theories. But for a long time, people didn't really believe that there was such a thing as a gravitational wave, or that moving masses around would warp space and time. And people became really convinced at a conference in North Carolina in 1957. And then the ideas for detecting it came from Joe Weber and Ray Weiss in the following decades. And a lot more work went on, but the big effort in the US started in the early 80s. And then finally, the National Science Foundation agreed to fund this project at the level of around $300 million in the 1990s. And the project called LIGO started. LIGO stands for Laser Interferometer, which is the animation I just showed you, Gravitational Wave Observatory. And Steve Jobs came out with the iPod around then, so we put an I in front of LIGO. We thought it would add some kind of excitement to it, because we weren't detecting any signals. No. I don't think it worked. So we did. And so then we had to change the letter every time we upgraded the instrument, whereas Steve Jobs just changed the version numbers. So this was initial, this one we called enhanced, and then a few years ago we started up a different thing called advanced, and if we get any better, we've sort of run out of acronyms. I don't know what to do. We'll have to have beyond advanced, super duper. That finally got built a couple of years ago after all the parts went in, and we started taking data in September of 2015. Okay, so that's the short history of how it goes. Now, to fully understand the impact of what happened, I have to tell you a little bit about time and distance, basically how big is the universe. And so this is one of our nation's great poets, and I think this was written soon after the discovery of general relativity. And I'm not sure if he understood general relativity, but it might be he was feeling it, and so he put this into one of his plays. I'm from here. These stars don't mean it's a special place. It's just these are all my favorite restaurants on Google Maps. And this is all I've got. So one of our detectors is here in Washington State, a few hours east of Seattle. And then the other one is here in Louisiana, about an hour north of New Orleans. And the distance between those two is about 3,000 kilometers. And at the speed of light, that takes about 1/100 of a second. Yeah. And so that's the size of the US. I'm sorry, I love these animations, so I put them all over. They have no scientific purpose. The moon is about the same size as the United States. And it takes light 10 milliseconds to get across the US, and it's about 1.5 seconds to get to the moon. So the moon is about 100 times farther away from California than California is from New York. That's the way to think about it. The solar system, so now you see why I brought up the Tennessee Williams quote. So now I'm counting things, distances in terms of the time it takes to go if you're traveling at the speed of light, which is very fast. I don't know how, very, very, very fast. I don't know how else to say it, but a lot of varies on top of it. So the solar system, there's all this, by the way, so there's all this controversy about Pluto. I am from that university, but I want to say, like, I'm not responsible for anything about Pluto or planets. And Pluto's a planet or not a planet, and now they say there's a new planet which may or may not be there. Please don't ask me about planets. That guy is down the hall, and I don't know about it. I don't know about it. So 3 light days, and it could be like 3.5 light days if you think that there's a new planet out there that we can't see. That's the size of the solar system. The galaxy, the Milky Way galaxy, how many people have seen the Milky Way galaxy at night? All right. This is the advantage of being here instead of Boston, Los Angeles, New Orleans. None of these places, you can see the Milky Way galaxy. You look up at night, and the sky is orange from the city lights, and that's it. All you see is sodium lights. All right, so you understand what I'm saying. The Milky Way is vast and beautiful. And here we are. We're out here sort of in the suburbs of the Milky Way. This is downtown. The distance, now, check this out. So this is 1.5 seconds to the moon. Wow. I don't know who that would be. Is that for me? No. 3 light days across the solar system. And from where we are to the center of the Milky Way, 70,000 years. So the Milky Way galaxy is super big. I don't even know how to imagine that in my mind. Very big, very, very big. And, well, there are things bigger. But 100 years ago, when Einstein was getting his theory together, people thought the Milky Way was the whole universe, that if you could travel at the speed of light for about 100,000 years, maybe, or 50,000 years, you'd get to the edge of the universe. Turned out to be not true. One of the things that I'm going to talk about are black holes. And I had to use this font because when I think about black holes, all I can think about is these bad science fiction movies from the 60s. Oh no, black holes and aliens from outer space. And everything else I'm going to tell you about seems a little bit like science fiction because it's none of the things, you wouldn't think that they're real. It's nothing that you really worry about. Black hole is a thing that's so incredible. It's taking something which is, let's say, 10 or 20 times heavier than the sun, or let's say thousands of times heavier than the Earth, and squeezing it down until it's smaller than the state of Colorado. And when you put that much mass into a small space, it's so heavy that if you have a laser pointer and you try to shoot it, well, none of these things actually happen. There's no people inside of black holes with laser pointers. But if you imagine that there were, if you did this, the light wouldn't even get out. You know, the light itself would be trapped by gravity inside the black hole. That's why it's black. No light gets out. This is just from a movie I saw. But it's not as fake as you might think. There was this movie, Interstellar. Did anybody see that? Oh, good. You know, I have to say this. I was in the original version of the storyboard of that movie. I was in the introductory scene, and I gave these people a tour of my lab, and there was a line in the storyboard that said, and I'm not kidding here, it said, "the handsome and charming leader of the LIGO collaboration," and then blah, 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 I don't know what else it said. And I said, oh, that's me. Who's going to play me? Maybe this guy. And at the time, I think they were humoring me, and they said, yeah, sure. Yeah, he'll play you. I need to know. Anyway, Spielberg left the project. We got a new director. He took it in a different direction, and I was no longer included. This is Kip Thorne, one of the theoretical physicists who's really been pioneering this field for years. He's doing one of the toughest things he does, which is work with Hollywood actresses and on the chalkboard. Jessica Chastain. This is Chris Nolan, who, it's interesting. I thought he's a director of movies. What has he got to do with anything that we do? As it turns out, he was very interested in how it is that we actually look for signals, given that we have so much noise. And the reason is, when he processes sounds for his movies, he's a really hands-on guy. So he's in there actually turning the knobs and adjusting the sound. So I've sent him a bunch of ringtones of our signals now, hand-tailored, and he thinks that's pretty cool. I thought it's sort of dull, but as it turned out, it actually had a use. It sounds like that's frivolous, but I learned some things about signal processing and finding signals along the way, which I'll tell you about. So black holes are black, and you may have heard these things about so-called dark matter and dark energy. What you should think about when people say that dark things, it's really invisible. It's not dark. It's not black, anyway. It's just we can't see them. And this is a pie chart. I like making pie charts. And this is, the orange stuff is us, everything in this room, and everything that we can see. And we think the rest of the universe, this much of it, is made out of dark matter, which it doesn't look like this, and dark energy, which is not blue. And this is an animation I like. Yeah. All right. Well, no, there was no gasps. Not as good as I thought. So this is the jelly bean model of this. And in this, we are all these brightly colored jelly beans, and the dark matter is the rest of the things. So this, you can imagine, this is the state of our knowledge of the universe these days, jelly bean model. All right. So I was talking about space and time. And we think, based on our measurements of the microwave radiation, that the universe is about 14 billion years old. And that means that the light from the earliest times in the universe has been traveling for 13 to 14 billion years by the time it gets to us. Or the light that we're getting now, at most, could have come from that far away. And now I've told you that the Milky Way galaxy is roughly 100,000 light years across. And that's a tiny, tiny fraction of this. 100,000, not even a million, and a million is even less than 2 million, and so on. Really small. So we're just here at the edge, and we've got our satellites, and we're trying to peer all the way back into here. And it's really hard, because the things from back here are faint, and there's a lot of things in the way. But as it turns out, it's not as hard as we thought. So I'm going to tell you a little bit about our experiment and this device. And it would be a bit complicated. I'll tell you anyway. But this is the image you should have in mind. This is a typical Rube Goldberg type of cartoon that expresses the way we do our measurements. Like I said, we're trying to measure this super tiny number, which is a motion of, we're measuring something about the weight of not the weight of a laptop. Well, not also the weight, somewhere in between the weight of a laptop and the weight of me, moving by amount which is something like 1,000 times smaller than the nucleus of an atom, or 1 billion times smaller than normal atoms, something like that. So it's such an incredibly small amount of motion. Everything in the world conspires to get in our way, and so we build a bunch of things that look like this, except for they're more sciencey. And they let us measure things and remove the disturbance. And there are a lot of people working on it, and these are those people here, roughly speaking. Plus, like I said, it's 900 others. So this is our device. This is a lot like the first cartoon I showed you, the animation. But this is in lower resolution because it's an older picture. But it has a little bit more detail. So there's a laser, it comes in. And like I said before, it gets split by this beam splitter, and half of it goes this way and this way. This laser is very powerful. And it's hard to express it in a meaningful way. This laser in my hand is not very powerful. It feels bright. If I put it in my eye, it would be bright. Don't put lasers in your eyes. But mostly, it would not blow up your eyeball or something like that, because it's mostly a safe thing that you can. Not everything on the internet is safe, but laser pointers mostly are. But the lasers we use here are roughly 10,000 times more powerful than this. It's like using 10,000 laser pointers. And if you use something that's just 100 times more powerful than this, as I find out, it burns all the hair off your knuckles if you stick it in the beam. So don't do that. It smells like burnt hair. And it burns holes in your T-shirt because our laser is invisible. So when it happens, you don't really see it. It's not like blue. Our laser isn't red. It's infrared. It's invisible. With something 100 times more powerful than this, you can do a pretty good experiment, but you won't find any signals at all from outer space. In order to be really, really sensitive and find black holes, you need a 10,000 times more powerful laser. And at that point, if you stick your hand in the beam, you'll be fingerless physicist, sadly. We don't have any of those. We're very safe. But you have to be careful. So now imagine we have this system. There's a laser. It bounces around in all these systems. And when you make you may have always wondered, what happens if I make two mirrors face each other and I stand in the middle? Will my reflection just, if I'm standing there and then I run out of the way really quickly, will my reflection just bounce around all the time? You may not wonder this. So in the time before internet, we didn't have any video games. We would just make our own fun like this. And it turns out that's true. Light bounces around between two mirrors for a long time. And so to build up the laser power in here, we make two mirrors face each other, and the light in here bounces around a few hundred times. And that ups the effective laser power we have. It gives us more signal. It's sort of like a balloon, but for laser light. So you put a lot of laser in there, the balloon just expands, and then eventually the balloon forms a little leak and some of the light comes out. And so we start off with 100 watts of power in here, and we end up with maybe 100 kilowatts of power in here. So really a lot. our system is very big. It's a few miles on each side, and it's completely empty. We use a bunch of vacuum pumps to pull all the gas out of it so that the pressure inside of the tubes is something like 1,000th of 1 billionth of the pressure that you have out here. There's almost no molecules left in it. And the reason we do that is we want the laser light to go straight and come back in without bouncing around off the gas. So it's a big steel thing like this. That's what it looks like. And yeah, this is the one in Washington. It's in this Department of Energy site. Everything's brown. There's no trees. And there's this one in Louisiana. Everything is green. It's a swamp. And I don't know. I was trying to make it sound better, but it's a swamp. It's like a swamp. It's got a lot of frogs and snakes and things. And you have to be ready to deal with it. Cockroaches and mosquitoes and so on, and frogs. It's an exhausting problem. Science is not all about lasers and black holes. It's more about frogs and snakes and mosquitoes than anything else. So inside, this is a regular-sized person, and this is one of the mirrors we have, and they're shining a light on it. You can see sort of what the size of the mirror is. It's about this big, and it weighs about 100 pounds. This is, like you've seen in the movies, NASA control rooms. There's a lot of displays, and usually a lot of people working in there. Here, there's just one person working, because it's after midnight, and everyone else has gone home. There's just the graduate students, because they're paid the least. So they just keep on working. I don't know. This is the control room in Louisiana in the daytime. A few people are working here because it's before 5 p.m. But roughly, this is the scene in both of this is basically the scene in 2015 when we were turning our systems on. And I want to a little bit put you in the mindset, so I'll repeat some of these things. So the idea started in the 60s. We had this sort of boy who cries wolf moment in the early 70s. And so we were all feeling very nervous that we have to be really careful. We never want to announce that we've had a signal if we're wrong, because you cannot cry wolf 50 times, once, twice, eventually. I don't know if that's a good analogy either. I don't know who's the wolf here. Anyway, we would want to be very careful. But it had been now 50 years that people have been hunting for gravitational wave signals from space, and they haven't found anything. And then over the course of 50 years, a lot of people they get into school, they work really hard for a few decades, and they quit, goes on, new people show up, they get told this same story that I got told. We've never found anything before, but we know a lot of things now that we didn't before, and next year is going to be the year when this is going to happen to you. And I would tell people this. I was recruiting students for years, maybe a decade before this time, and every few years I would say, last year when I said this, I was wrong, but this year, I really know what I'm talking about, not like all those people before. This year, if you get involved, you will be the first ones to have a real gravitational signal from outer space in your hands. And no one believed me anyway. So we've turned on the system. It's September 14th of 2015. And let's see if this works. No. Oh. Science is hard. Let's try this again. All right. So our detectors operate in the audio band, so they're just detecting vibrations of the space-time. I say that, but mostly they're detecting vibrations of our equipment and the environment, and there's little or no vibration of space-time. We would just wish. So we listen to the noise all the time, and it sounds like that. And that's one of the vibrations of one of our pieces of glass and metal. So I did this analysis that I described to Chris Nolan. I removed some of the lines, some of the noise that we get from the power lines and the walls, and some of the oscillations of some of the wires and pieces of electronics we have. And I looked at just the low frequency noise, and this is what that sounds like. Let me play it in a little bit more visual way. Just a second. Let's go over here. That is not it. Well, okay, well, hold on. Maybe that's not so bad. So you heard right then, that was a frequency chirp. And in that one, the frequency was going down. And that's, yeah, and that happens because when Jimi Hendrix is playing that part, he moves his finger from the close part of the guitar all the way down like this. And the string is allowed to become longer, the part of the string that's vibrating. And the reason that happens is because the frequency of the vibration has to do with the length of the string. Okay, anyway. Let me play you what I wanted to play you. Should be one of these. Let's see this one. Okay. Right. Where's the rest of it? Maybe it'll show up. No, terrible. Zoom out. All right, let's try that again. Let me loop it like here. So you hear that little thump? So when the thump is not playing, that's the vibration of our instrument and the random noise that comes in from trying to measure things. And this thump, and it's in stereo, so the top one is the one in Washington, and the bottom one is the one in Louisiana. That's the first ever signal from black holes in gravitational waves to hit the Earth. And that is the signal from September 14th. And it's just that short. It's a little thump. And yeah, thump. And so here it is visually. All right. It's a Mac, so it has some bugs. This is the noise, and this is the signal on top of it. It's this chirp, and you can see that please shut up. The frequency goes up, and there's a whump. And the whump is when the black holes hit each other and change from two black holes into one black hole. And this is a picture of it evolving in time. It takes a couple tenths of a second, and it goes from the low bass frequencies here up to the frequency that you hear, and sort of whoops up like this. And so it's sort of the opposite of the Hendrix sound. We took our best calculations of the signal and subtracted it out of the measured data, and what's left just looks like random noise. And so this is a really beautiful example that what we've seen is a real vibration of space-time from binary black holes. So this is just a movie of it overlaid on a star field. So this is a big black hole and a slightly smaller black hole orbiting each other, and the star field in the background is just there to show you how light comes through, how it would look like if there was a bunch of stars behind. And you can see the space is getting warped in the orbit. This is the early part of the chirp. They sure go around for a long time. And then it gets crazy. Bloop. Yeah. This is another animation. This will take a second. In this one, you see the two black holes. This is how much this space-time is curved below them. This is, I guess, sort of, nothing so surprising is going on here. Space is curved as we expect. Where it gets crazy is around the point where the waveform hits here. And it gets wild, and the curvature of the space goes in the opposite direction from what we're used to. And this is a fake slowdown. You can see the real time up there. Yeah, it looks like a monster. Yeah, to me, the fact that this kind of calculation can be done and that we can measure something like this, it means all of a sudden, on that day in September, we went from having no knowledge of how this works to all of a sudden be able to measure how these things work in the universe. And and you can now get it as a ringtone on your phone. So I don't know, that's modern times. So this, like you saw, this is the inspiraling part, and the whoomp at the end happens where the two black holes merge, and then at the end it shakes. And the shaking frequency, the frequency at which you heard the thumping, has to do with how big the black hole is, basically. It has to do with how long it takes light to travel around the outside of it. And so if you have a black hole at the end which is twice as heavy as what we got, then the frequency will be 2 times lower, just like it would be with guitar strings. We're still working on the processes to find out where these things came from. It's tough, given that we only have 2 detectors, one each side of the US, to figure out where the thing came from in the sky, but we think it came from the south. And so the signal came to Louisiana first, and then it went to Washington about 6 or 7 milliseconds later. And the reason basically is because having 2 detectors is just 2 ears. And with 2 ears, you can tell if something's from here or from here, but it's tough to tell if something is from here or here. And so we'd be much better off, for example, if we had an extra ear here and maybe one in the back, and then you could tell with 4 ears really if somebody was attacking you, which direction they're coming from. And we'd also like to have more gravitational ears. So this thing, after looking at the signal and a lot of smart people analyzing it, they found the mass of the final black hole was 62. That means it's 62 times heavier than the sun. And the signal came from 1.3 billion light years away. So the coincidence of this thing is pretty remarkable. So it's a Sunday night, and that picture I showed you with one lonely person working there, that person is there, and there's another one in Louisiana, and they're just working. This black hole merged 1.3 billion years ago. They're still working, and the detector is not working because they're still tinkering with it. And it's something like close to 3 a.m. in Washington, and 2 a.m., maybe 2 a.m. and maybe 4 a.m. in Louisiana. Just before they go home, they switch the on button back so that the detector starts listening. And while they're still driving home that night, this first signal that we've ever detected comes through, and probably one of the best signals we'll ever get. And the timing of like 45 minutes after a travel of 1.3 billion years is a pretty lucky pull, I think. Let me skip forward a bit. There are some ideas to get more ears going, as I said. There are projects already underway in Italy and southern Japan and central India. These two are different projects. The one in India, which should come on in 7 or 8 years, is meant to be a copy of the American LIGO ones. We've shipped some of our parts down there, and they're putting in half the money. And we think that should do a lot for us. This is a painting that I saw in the museum where I went to school. And it's about this size, actually. This is pretty close to lifelike. And I think this is the translation from the French, but I don't know French. So anyway, I think that's what he's saying. He's saying something like, this is time going from right to left. And when we start off, we don't know what's going on. And we wonder, where did we come from, and what kind of people are we, and what are we going to do next? And I don't know what the chicken means. I don't know if that's meaningful. But we always wonder this in science. Like, what are we doing now? What just happened? And what are we going to do next? And so I'll tell you about next. We here are working in the audio band using our ground-based system. We also want to put interferometers in space to detect the signals from much more massive things from early in the universe. We want to use the tools of radio astronomy to see how much the galaxy is stretching and warping in order to look for the collisions of galaxies and supermassive things. And then finally, we'd like to see if there are gravitational signals from the Big Bang at the beginning of the universe and see if they've distorted the radiation that we're getting in other bands. So we have a lot of hopes for doing a whole new branch of astrophysics using gravity. In the US, for our project, well, we've detected 2 black holes. We got one on September 14th, and then we've got one during Christmas dinner in 2015. And then we've worked to improve our detectors for a year, and we've just switched them on again. And we hope, more black holes, I guess. And even, I don't know what else, but even more, the unknown, whatever that is. And hopefully, within 10 years, we'll have a bunch of these things going and be able to find out much more about them. But we really think we ought to go better. And this one signal that we got is from 1.3 billion light years away. And we think the universe is 13 billion light years old. And so we only have to make our system 10 times better, roughly. And we would be able to detect black holes from the beginning of the universe. And then there's no more. That's the end. You're at the edge of the pool. And if we can do that, that means we would be detecting all the black holes in the universe all the time. And it would be this step from nothing all the time to a full plate of all the signals. And once we get something like that, it's a magic. Have anybody seen this movie Daredevil? Oh, it's terrible. I can't say that. That's being recorded, isn't it? It's wonderful. Whatever. Wonderful, terrible. Anyway, the way Daredevil works is he's blind. He's a blind superhero, but his hearing is really good. And so he listens for sounds, and he listens for how those sounds deflect off of things. And that tells him what's in his environment, and then he does kung fu, right? And that's basically our plan, the Daredevil plan. And you can see this if you're in a dark room. So you go in a dark room, like this one could be, and you close your eyes, and you can make some sounds like, and you listen for how the vibrations sound when they get back to you. And that tells you a little bit about how big the room is, and how soft the walls are, and if there's a lot of people in the room. This room will sound different if there's nobody in here. And if you're in a closet and you do that, that's different than if you're in your bedroom or if you're in the bathroom. That's why people like to sing in the shower, because the echo is a little bit different. And our aim is to use this kind of clucking noise that comes from all the black holes in the universe to map out what's the universe really about. What's the structure? How big is it? How big was it in the past? Is it getting bigger now? I mean, we can use this as a kind of sonar system, black hole sonar system, to tell us everything about how the universe is made up of. And to me, it's pretty amazing. We can go from having nothing to perhaps having the Daredevil dream from black holes in just a few years. So this is a picture of the universe from the late 90s when I was getting going. And there was this blue picture of the gravitational wave world, and there was all these low-resolution pictures of the universe. Still, every time somebody turned on an instrument, it was fantastic. They detected all kinds of stuff. And I worked in this area for about 7 years or so. And then I went to a conference one time, and there were some guys who had made a swimming. This is not actually pretty much like this. They had made a swimming pool out in the middle of the desert, and they had put a bunch of cameras to look in the swimming pool to see if flashes of light happened there once in a while. And they used that to detect cosmic rays. So in about a week, they had signals going already. I said, come on, this is not fair. We've been working for 50 years, $300 million. We've got nothing. Every other wavelength has got something in the sky. And, well, time has passed. Every other field has gotten better. you know, it's very dark. And, you know, I'm a pretty good person. I deserve some signals, I figure, after all this time. And for me, after roughly 20 years now, oh, it disappeared already. It was one of my last animations. Let's try again. For me, after 20 years, finally, we got this little spot now. And we now can also place our image of the sky alongside the other people's. And we are also astronomers now. And soon, we will return to you with a complicated image like this, like one of these, but it will be even more grand. It'll be like the Daredevil movie. Yeah. Thank you very much.
That was great. So we have some time for questions. So raise your hands, and I'll call on you, and then we'll go from there. So please.
How do you know where the signal's coming from? Which black holes are colliding, producing the gravitational wave?
So the question was, how do you know where the signals are coming from? Which black holes are actually producing the gravitational waves?
Very roughly, it's just to do with the delay, and it would be a little bit like the math that goes on in people's brains when you turn like this and you turn like this, and you can tell which direction a sound is coming from by which ear gets it first. Mathematically, we do it by adjusting the time delay in our data streams to figure out the directionality. We can do a little bit better than that because the signal has more complexity than being a steady tone. It actually chirps in frequency, and it affects the different arms of our L-shaped instrument differently. But more or less, it has to do with the time delay. So the bigger the distances we can get between detectors, the more precisely we can tell the direction. We can tell something about what kind of black holes were, like how heavy they were and from how long ago, by looking at the strength of the signal and also by the frequency of the sound, more or less.
So the question was about gravitons.
Yeah. At the moment we're not. And the reason for that is that the signals that we get have so many billions and billions and billions of gravitons that we couldn't tell the difference of a graviton more or less in our system. And it has to do with how powerful our signals are. There's no way we could detect a single graviton. We're just now getting the most powerful events in the universe. So it's, centuries away before we'd be getting something like that.
The squeezed light system you're looking at installing, could you elaborate on that a bit?
So the question was about the squeeze light system.
Yeah. I have some graphics. It's as if you were a plant in the audience. So one of the limits to how well we can detect things has to do with the fact that of quantum mechanics, and it means quantum mechanics is telling you about, in the case of light, that if you have a light source, the light comes to you in little packets. And so if you have like a really, really dim laser pointer, and you did point it at your eye, even though I said don't point it at your eye, you would be able to detect the individual photons, which are the quantum particles of light hitting your eye. Anyway, don't try that. And that's a problem for us. It means I filtered that out of the sound that I played you, but if you took the photodetector signal there, photodiode, and you took the electricity and you just put it into your headphones and listened to it, it would have a kind of hiss. And that hiss is the sort of popcorn pitter-patter of the photons hitting your detector. And that's a kind of fundamental limit for detecting anything, any kind of signals. But it turns out the laws of quantum mechanics don't mean that you cannot do better than this kind of pitter-patter photon limit. The laws of quantum mechanics really tell you something like, if you try to measure something really well, you'll disturb it somewhat, and it disturbs your measurement. And that's not so surprising. If I tried to measure the position of something moving around on here, and I shot it with a 100-watt laser, of course it would just blast it away. You can't blast things when you try to measure them. And in the same way, if you try to put too much laser power into the system, it actually shakes the mirrors around too much, the pressure from the light. Squeeze light is a way to modify the statistics of quantum mechanics. And quantum mechanics only tells you that you have a fixed amount of uncertainty, but it doesn't tell you that you have to have that uncertainty all the time. It just says, on average, you have to have this amount of uncertainty. And we are only looking for the gravitational wave signals to stretch the space-time in between the mirrors and the central place. But we're not so much interested in how much the laser power is changing. We're just interested in the one variable, which is the stretching of the space-time. So we can ignore all the other ones. So the squeeze light technique is a way to change the way the statistics of the light work so that it makes everything much more uncertain, but it reduces the uncertainty in the one signal or one kind of degree of freedom we're looking for. And it's a little bit a way of sweeping things under the rug. So we're not really breaking any laws, we're just bending the laws, I guess. And it's possible, and it's been now demonstrated, that we can at least double our sensitivity in this way. It's hard, but it's doable.
Telescopes are looking at a certain part of the universe, I guess, but are your detectors non-directional? They're looking at the entire universe?
So the question was, do the gravitational wave observatories look at a particular direction or the entire universe?
Mostly our detectors look in all directions. You can imagine, well, let's see. So if you have a megaphone and you talk through it, your voice mostly beams in one direction, but it's not too narrow. It's not like with a laser pointer where your signal is one direction. So with things that have a very small wavelength like light, you can point things really narrowly. But with things like gravitational waves, where the wavelengths are really long, like with sound or something like that, you can't do it. And so the way to imagine it is, here's this globe, and we've put these little L-shaped detectors on a couple places, and the pattern, the directions in which we're sensitive, looks sort of like a peanut. And so you have a globe, and imagine you stick a few peanuts into it, and those peanuts are the patterns in which we're sensitive. And just like peanuts, peanuts sort of shrinks down in the middle. And so there's a couple of directions which are in the plane of the detector where we're not so sensitive. But if you think about what a weird story. If you think about overlapping a bunch of translucent peanuts, and imagine what that shape looks like, they sort of cover each other's holes. And so you end up being able, if you have 4 or 5 of these things, you would be sensitive in all directions with all the peanuts.
Earlier, a gentleman asked a question about the recent article in Scientific American raising questions about the inflationary period after the Big Bang. And one of the issues that they raised in the article was the lack of finding gravitational waves from that period of inflation. Are the instruments you're working with, would they be sensitive to that, the gravitational waves, if any, that existed from inflation?
So the question was whether these instruments are sensitive to the gravitational waves that come from inflation.
I really hope yes, but I think even in my most optimistic days, I think they won't. And there's several reasons for this. Not everybody believes that the theory of inflation is true as is. And it may yet turn out that the amount of gravitational perturbations produced at the time of inflation, which was super early in the birth of the universe, it might be that very little gravitational perturbations were produced. And if that's true, we could still detect it with one of these space detectors, but I guess it would be another 50 years because our technology is just not there yet. But even that is for a very hopeful scenario. And unless the theory of inflation is a lot more complex than we expect, or that most of us expect, we wouldn't be able to detect those signals with these kind of detectors. However, this thing on the left, which is looking for swirls in the radiation, electromagnetic radiation all over the sky, they still do have a going chance. But I would say if they don't find anything in the next 15 years, we'll have to rethink how this whole Big Bang story goes.
Can you explain, please, how it is that you concluded that the thump that you heard comes from a black hole?
So the question is, how do we know that that thump is actually coming from a black hole?
Yeah, so roughly speaking, it is never, whenever there's a thump, more or less, it is never from black holes. All of the thumps that we get come from something else. And so most of the time, the thump is like there was a car nearby, or somebody pressed a button they weren't supposed to, or there was some sort of animal that has crashed into the building, one of those things. And so over the years, we've developed many, many different sensors to catch all of these different things, tumbleweed, animals, and so on. And for each of those things, we have a specific signature, so we can really identify it and say, oh yeah, that's that thing again. And those let us rule out a whole host of Earth-based problems. And even exotic things like maybe there was a lightning strike in Kansas which made a magnetic signal that went to both places and made trouble, or there happened to be a trucker with a CB and another one in the other part of the country, and they were saying the same thing, and it was coincident or something like that. Even those things, we can find what they were and get rid of them. And so basically what we do is we go through all of those different checks we have, and we come up with all the different explanations we can, and exclude that it's an environmental effect. But then we also do a detailed analysis of the actual waveform that we get. And it's extremely hard to make a thing that looks like the signal I showed you that so precisely matches the predictions of the Einstein theory to a very precise level. And none of us know how to do that, even those of us who've been working around with the details of the instrument for years. And I disbelieved that it was real for about 3 weeks. And I went through, I had gone to this conspiracy theory edge where I was thinking if there were 2 disgruntled employees who were doing a Mission Impossible type thing where they were dressed in black and suspended down and were touching things and the cameras were turned off, could they have done it? And we even ruled out Mission Impossible type of scenarios. And finally, the stuff that was left was too oddball for me. I felt like, if I had blacked out and gotten disgruntled and then went off and did this, maybe I could have done it. But you'd need 2 or 3 people like that to make it work in different parts of the country. And then once we started getting more signals, it didn't seem so likely. You'd have to go Mission Impossible every couple months.
Your answer is that it conforms to Einstein's theory of what it should look like.
But, even if it didn't, we would have found it and acknowledged it as a gravitational wave. So this one happened to be from black holes, which are a thing that you can well predict using the basic Einstein's general relativity. But the main point is that we've ruled out all other sources of signals coming in from the environment. And so even if it was a thing that no one had ever predicted, if it had been so loud, we would still find it. And instead of showing you these movies about black holes, we would be scratching our heads about where it came from.
And I'm just going to make a comment. The experimenters, when this all happened, they didn't really believe it. And the theorists, we were all convinced within like an hour that this was real, which tells you something about the communities. Okay, we'll take one last question.
Cold, low-temperature experiments like the Xenon 100, what is the frequency response? What is the energy range that you're looking at?
So the question was the frequency response of Xenon 100, which is a dark matter experiment.
Yeah, those are different. So the things we're looking for is just a stretching of space and time from events that happened, say, a billion years ago. And experiments like the xenon and so on, which are looking for invisible dark matter, that's more like a really heavy subatomic particle comes flying through their detector and impacts some of the molecules, some of the xenon molecules that they've got. And so it's a different source that they're looking for. The energies they're looking at are something like, roughly energies of protons or something like that. And the energies of the black holes that we were looking at, they're more energetic than all the energy put out by all the stars in the universe for a tenth of a second.
Okay. On that note, I'd like to thank you all for coming, and let's thank Rana.